Hello class. Today we're going to do a flipped classroom on parts of the atom, and this will include all the different subatomic particles as well as the concept of isotopes and calculating average atomic mass. Now if that all seems confusing and scary, don't worry, I'm going to make this as simple as possible. First of all, let's talk about the way the atom is represented. Now the atom was not developed immediately, it was developed over time through lots of scientists over history. It started as a concept of that they were possibly indivisible hard spheres, and then later on it grew into the concept of, okay, wait, they're not actually hard spheres, and that they have different parts to them. But everyone accepts today that the center of the atom, which we call the nucleus, is where you find the protons and the neutrons. Then there's a lot of empty space, and then somewhere on the outside you find the electrons. And then in a later edition of these videos, I'm going to talk about where the electrons exactly are located. But for now, let's just say they're outside the nucleus somewhere. So there are many scientists, as I said, that got involved in the understanding of the concept of the atom, but the one I want to focus on mostly today is Rutherford. Rutherford, also called the father of the atom, came up with two main conclusions about the atom. That number one, that the atom is mostly empty space, as you can see from the picture. He did a gold foil experiment where he shot alpha particles at a piece of gold foil, and most of them went right through, proving that, yes, indeed, the atom is mostly just a lot of emptiness. But as you get close enough to the center, it was found that it has a dense positive center. That this entire section here is very dense and has an overall positive charge. And that was Rutherford's conclusions. So now let's get on to more specifics about the atom. Let's talk about the different parts of the atom. So in this atomic chart here, I have three sections. I have subatomic particles, which are the different parts inside an atom. Their relative charge, because we don't care about their exact charge, we just want to give a relative number, and also their relative mass. So first we have protons. Now what are protons? They are positive charges inside the nucleus of an atom, so they are given a charge of +1. And relatively, and remember we're talking about relative mass because you can't actually weigh a proton. There's no balance small enough. We're going to give it the atomic mass of 1, and the units we're going to use are also a made-up unit. We call them AMU, which is atomic mass units. Next we have the neutrons, which are also found in the center of the atom. They don't have a charge. They're neutral. That's why they're called neutrons. So they have no charge. But relatively speaking, they're about the same size as a proton. They're only slightly bigger in mass, but to one significant figure, even to two significant figures, it's still only 1 AMU. And then finally we have the electrons, which are located outside the nucleus. They have a relative charge of -1. So they are the exact opposite in charge of the proton. So it's safe to say that electrons and protons have the same magnitude of charge. They're both 1, but exact opposite charge, -1 versus +1. However, where the real difference is the size, the mass of an electron. It would take over 1,836 electrons to equal the mass of one proton. So its relative mass is 1 over 1836, but that's a ridiculous number. We're just going to round that to 0. We're going to say, you know what, electrons are so small, let's just call them 0. Which means I don't care if we had 100 or even 300 electrons in a sample, it wouldn't make a dent in the actual relative mass because the protons are so much bigger. If you want a relative scale for comparison, you could say that, relatively speaking, if an electron were the size and mass of a pea, a proton would likely be the size and mass of a basketball. So now I want to talk about atomic symbols. So as you can see here, I've shown an atomic symbol for the letter C, which stands for carbon. I also want to show it to you in the reference table. Here it is at the top here. There's carbon. Now, by the way, if you don't know that carbon is the letter C, on the next page in the reference table, there is a list of all of the atoms and their atomic symbols in order from atomic number up to 90. And the numbers I want to focus on here are only these two numbers for now. This number on the top left and the number here almost at the bottom left. Let's start with that one, the atomic number. carbon has the atomic number 6. And if you notice in the reference table, it is the only element that has 6 as its atomic number. There is no other element with that number. So what does that mean? Well, the atomic number is the number of protons. Hold on one second. So carbon has the atomic number 6. It has 6 protons. The number on top is called the atomic mass, or atomic weight. And it has a mass of 12.011, or 12.011 AMU. Now, this might be a little confusing because we just said in the previous section that protons weigh 1, and neutrons weigh 1, and electrons weigh nothing. So where are we getting a decimal from? Well, some could argue that I said, well, you know, it wasn't exactly 1, so you're rounding it. But if you look throughout the table, you'll see that every element has masses that are decimals. Here, let's take a closer look at some of them. Nickel is 58.693. Copper is 63.546. They're nowhere near whole numbers. So where are we getting these weird decimals from? Well, the truth is that they are average atomic masses. They're not just atomic masses, they're averages, which means there's more than one version of carbon. As a matter of fact, there are 3 versions of carbon. They are carbon 12, which you can write the hyphen notation like this, or the symbol notation, carbon 13, and carbon 14. So let me explain how we're getting these different versions of carbon. As I said, these are isotopes of carbon. An isotope, and you should write this definition down, is the same element but with a different mass. And the reason why it has a different mass is because isotopes have different number of neutrons. Other than that, the isotopes are identical. The protons are the same and the electrons are the same, only the neutrons are different. So how do we count the neutrons? How do we know how many neutrons there are in an atom? And for that matter, how do we know about the rest of the subatomic particles? Well, let's go to this example to start with. Carbon 12. I don't care that its mass is 12. The 6 is what I'm going to focus on. Carbon has 6 protons, and carbon only has 6 protons. But if carbon weighs 12, and remember, each proton weighs 1, that means that half of the weight is because of the protons. What's the rest of it from? Well, if you subtract 12 minus 6, you get 6 left. What's that 6? Those are the 6 neutrons. So if you add up 6 protons, plus 1 each, and 6 neutrons, also 1 each, 6 and 6 is 12. Now here is carbon 13. Carbon 13 still has 6 protons. They all do. But if it weighs 13, that must mean, it's 13 minus 6, it must have 7 neutrons. And again, 6 plus 7 is 13. And then carbon 14 has 8 neutrons. Notice when we do these calculations, we don't even care about the number of electrons. And remember why? Because electrons don't weigh anything. But what if you still wanted to know the number of electrons? Well, that's easy. Because in any atom, the number of protons and the number of electrons must be equal. So carbon has 6 protons, no matter which isotope you're talking about. Carbon has 6 electrons, no matter which isotope you're talking about. But the neutrons, well, that's going to depend on which isotope you're looking at. Are you looking at carbon 13, 14, or carbon 12? However, I could ask the question, which of these isotopes is the most common? Well, remember we found out earlier that carbon had the average atomic mass of 12.011. Based on that number, which one do you think is the most common version of carbon? If you said 12, you'd be right. After all, that number is pretty close to 12. As a matter of fact, almost 99% of all carbons are carbon 12. There is very little of carbon 13 and 14 in any sample. Which now brings us to the last thing we're going to do today, and that is, how do you calculate the average atomic mass of an isotope? So for this example, I'm going to show you two versions of chlorine. There are only two versions of chlorine that exist in nature. They are chlorine-35, which again I could write like this. There's the isotope notation as opposed to the hyphen notation. And there's chlorine-37. Those are the only two naturally occurring isotopes. So I did some research and I looked up some information, and it turns out that chlorine-35, if you get its exact mass down to the fourth decimal place, weighs 34.9688. Remember, we said relatively these protons and neutrons weigh 1 each, so this is being much more accurate. And to 4 decimal places, chlorine-37 weighs 36.9659. I also looked up the natural abundance of these isotopes, and it turns out in any sample, and I mean anywhere in the world, 75.78% of all chlorines weigh 35, and the other 24.22% weigh 37. So if this were a test question, this whole chart would be given to you. You'd be given the isotopes, their mass, and their abundance. So how do you calculate the average? Well, this is how you do it. First, understand that percent is not really a number. Percent means out of 100. So what I'm going to do is I'm going to take this number and divide it by 100, or move it 2 decimal places to the left. So 75.78% becomes 0.7578. And 24.22% becomes 0.2422. Now all you have to do is multiply the abundance times the mass. Just multiply that by that and that by that. So 75.78 times 34.9688, that number up there. If I multiply it, I get 26.4993. And 0.2422, which is that divided by 100, times the mass, 36.9659, gives me 8.9531. What do I do with those two numbers? Add them together. And that will give you the average atomic mass, 35.4524, which, if I'm rounding to 4 significant figures, because after all, I'm limited by these numbers here only have 4, I'm going to round it to 35.45 AMU. So that's the average mass of chlorine in any sample. Now, the beautiful thing about this example is that I can confirm right now that I got the question right. If this were a question on any test and I was wondering, well, maybe I made a math error, how do I know that that's really the average of chlorine? Well, all I have to do is go to the reference table and look up chlorine. And sure enough, when I look at chlorine, the average atomic mass for chlorine, 35.453. What was my calculation? And again, mine only went to 4 significant figures, not 5. 35.45. Pretty good. The only confusion people sometimes get from this is that they think, oh, well, I'm doing an average, and I've done 2 isotopes. Maybe I should divide this number by 2. No, 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 don't do that. You've already divided this number by 100. You've done your division. You don't have 2 samples of chlorine. You have billions of samples of chlorine in one container, and we're just saying, okay, it's 75.78% of one and 24.22% of the other. Once you divide by 100, no more dividing. You are done. And that is our lesson on parts of the atom, isotopes, and calculating average atomic mass.